not hear it? It's pretty loud from what I can tell right now. You can't hear it coming out of that? Okay, maybe you want to move to that seat, because much louder it starts to hum. It's an inverse relationship between the volume in your ear and the distance from the speaker. It's actually an inverse square. So if you cut the distance in half, the volume goes up by a factor of 4. It's the inverse square relationship. It applies to a lot of physics. It's not really true, not the volume. The volume doesn't go up by a factor of 4, but the energy of the sound wave that's coming out of your speaker goes up by a factor of 4. You would think that would cause the volume to sound 4 times louder, but it's not. Volume actually has a logarithmic relationship with the energy of the sound wave. Unfortunately, that means that it doesn't get 4 times louder when you get 2 times closer to the speaker. Anyways, I got interested in science, physics, because I had a lot of interest in astronomy, black holes, all that kind of stuff, time travel. And as I started to research it in my young 20s, I realized that all the questions were really physics questions, and if I wanted to understand any of it, I had to really consider physics as a route to the answers to those things. So maybe you like it, like I did. Maybe you didn't. Maybe you don't. I don't know. But I'm just saying, I do find it very interesting. Outer space stuff is very, very fascinating. So that's what we're going to go over. We're going to go over the orbital lab, orbital motion lab. Can you hear better at that position? Can you hear better at that position? I'm okay. I mean, even from my ear, I can hear my volume of my ear. I guess it's projected towards me though, and maybe the sound of the fan. I don't know. I don't know that I can go much louder than that. I mean, I could stick it inside here. That really helps you. But now, unfortunately, Mr. Colton's room can probably hear me. Yeah. That's what we'll do. All right. So let me just do the attendance. It was 1, 2, 3, 4, 5. No, 1, 2, 3, 4. You're at 8. Joseph, I feel bad that I never take your attendance. I don't think it really matters, but I did today. Just now did. Only because I accidentally clicked on that other spot in my attendance. There we go. So Zoe is present. Carly would be remote present. Carly would be remote present. Remote present. There we go. Jaden, remote present. Ashley, present. Caitlin, remote present. Emma, remote absent. All right. I'm going to change my video camera. I think I have to just shut it off here. And now go to. In fact, I might want to comment that really the deepest history of physics and mathematics in the history of civilization, which doesn't go back just thousands of years, but tens of thousands of years. And it's debatable to potentially be hundreds of thousands of years, but history people don't want to admit that there's an awful lot of evidence that suggests that is true, that our civilization potentially goes back hundreds of thousands of years. But in either case, tens of thousands or hundreds of thousands, the deepest, again, reaches of physics and mathematics was applied to astrophysics. It was all applied to the sky. All of the not all of them, but the vast majority of mathematicians and science physics people, not back just to days of Aristotle, but well before Aristotle, they were always using their math abilities to chart what they would call the heavens, right? Chart the motions of the stars. So when you study this, you're really studying a very sacred knowledge that extends back, like I said, potentially hundreds of thousands of years. you're potentially thinking about things that people thought about back then, the same things. And you might wonder, why was so much time and effort put into such a topic? Anybody have any guesses? Why it was so important? Why was the stars and the planets such a huge, huge focus for all of the ancient civilizations, from Egyptians to Mayans to Aztecs? Yeah, what is it? Because it is a, yeah, like to do with like religious, is that what you mean? Yeah, totally. I would say there's a number of reasons why it was important. Spiritually, of course, there's a connection when you go back to, even the Egyptians or the Sumerians, or any of them. Any of them, they all had a belief. Even the Egyptians, of course, believed that the sun was their god, the sun god Ra, which I don't blame them. I mean, it clearly gives life, and I think they knew that without the sun, everything would die. But there was definitely an appreciation for the stars, not only from a religious point of view and a spiritual point of view, but navigationally, it became quite important because, of course, they didn't have the things that we had. They had to take boats, right? And so when you wanted to go somewhere in great distance, the only map that you had was the stars. So that was one reason to really understand how to use that map at night, because when it's completely dark and you're in the middle of a storm, which could easily throw your boat off course, it became vitally important that they knew how to use the map to guide them to where they needed to go. Their lives could be on the line, of course. Getting lost at sea is no joke. And then in addition to that, you have farming, agricultural applications where you need to know what the proper time of the year is to plant your seeds. You need to know what the proper time of the year is to harvest. All of that can be done at any time, of course, but if you really want to maximize the growth, the yield, what we call the crop yield, which is how much the field produces for you, you really have to know, if you want to optimize it, to get the most out of it. And sometimes this is for food for thousands of people, and it's the food that they're going to store and get them through the winter. You have to know exactly when to do those things. And it turns out that the stars and the path of the sun and such all provide knowledge about, times of the seasons and such. And so they can actually use, you might have heard of the what's it called? I can't think of it right now. The row of big stones. There's a big, like, circle, I meant, a big circle of stones. What's it called? Giant tall stones that are in a circle. I can't even think of it now. The Stonehenge, thank you. Yeah, I couldn't think of it. Those are usually thought of as to be like clocks, but they were using them with the stars, and they would the sun, I should say, cast certain shadows onto the floor, so they knew if the sunlight went right through the certain area and hit this spot on the grass or whatever it might have been, or go through this hole in the rock, that would mark the first day of spring, for example. Time to go plant our seeds. Interesting, interesting. But anyways, it certainly has a very deep from a history point of view, very deep past. All right, so let's tackle this question. The question was posed to you guys, which was, could we come up with a formula that gave us the physical speed of a planet going around some central object? So I think the assignment was relating to originally it asked you to do the moon speed, but then in the lab part where you were graphing it, that was related to the planets. I'm going to just do it related to the planets. I'm going to call this sun and call this the Earth. The point is that once you learn this, you can apply it to anything. These the math that we're using here, as long as the object's going in a circular path, then you can use this. If these formulas to predict all sorts of things. You can use these same formulas to calculate the mass of the Earth. That was one of the things I remember wondering when I was like 21, like reading in a science book that they knew the mass of the Earth. How is that possible? How do you know what the mass of the Earth is? Well, it's in the formula that you guys used, right? And it turns out you can solve for it if you know some other values, like how long it takes the moon to go around the Earth. That's something that you can use to calculate the mass of the Earth, interestingly. But anyways, these are universal laws. They can be used for Moons going around planets. They can be used for planets going around stars. They can be used for planets going around, I meant to say stars going around other stars, which, by the way, most stars are actually, this is a star, let's say, and this is a star. Well, stars, our sun is a star. They actually, most of the stars in the night sky, when you look up at night, are called binary star systems. So there's actually two stars, and they actually orbit around each other, orbit around their center of mass. If they're the same mass, then the center of mass is here, and they would just both orbit around the central imaginary point called the center of mass of the system. If one of them is a little heavier, a little more massive than the other star, then the center of mass and the point ends up being a little closer. They'll still both orbit around that point. This guy, this big one will wobble around that point, and this guy will also, they're kind of like this. I'm pointing out that almost all the stars that you look up at night are actually two stars. You can't tell because they're so far away, they merge together to form one dot. But if you could get in a spaceship and fly towards one of those stars, at some point you'd see that it breaks into two pieces of light, and you realize, oh, that's actually two stars. They're just so far away. Yep. Yep.
You're not presenting.
Oh, so sorry. Thank you. I appreciate you telling me that, though I didn't draw much, but I'd still be happy to show you. I just drew this here, indicating that I think I have to do that again. Sorry. That stars orbit around, there we go. They orbit around like this, a center spot. So if the two stars, if this was a star and this is a star, in outer space, you look at night and just see one star. But again, it's really two stars. They orbit around each other. If they're the same mass, just like we're actually going to be doing this stuff relatively soon. If you put a block on this side of a seesaw and another block on this side of the seesaw, and they weigh the same amount, they have the same mass, then the center of mass is right in the middle, and that's the center of mass is the point where you would put this, called the fulcrum, so that it balances. So in outer space, that center of mass point, imagine those two stars being on a seesaw again. That center of mass, if they're the same mass, is in the center, and they would orbit both around this point. If one is a little more massive, just like if we did a seesaw like this, and then we had a big heavy object here and a light object on this side, turns out that you would actually have to move that point, that balancing point, closer to the heavy one, and these could actually end up balancing. And for the star systems that are binary star systems, when you have one that's more massive, that point ends up shifting closer to the heavier one. This bigger one will orbit around that point, and so will the smaller one. They'll both orbit around that point. Anyways, what we're doing applies to, again, planets going around, moons going around planets, planets going around stars, stars going around stars, stars going around black holes going around black holes, stars in the galaxy going around the center of the galaxy, which is the giant black hole, the center of our galaxy, galaxies going around galaxies. As long as the motion is circular, and in a lot of cases it is, not all, for comets, the comet path is not a circle, it's an ellipse, and we'll talk about that later. As long as the motion is circular, in a lot of cases it is, you get to use these formulas. All right, so let's return to it. If we were asked to draw a free body diagram, should we draw the normal force? Yep. No. Yep, we wouldn't draw a normal force. The normal force is only a force that comes into play when you're in contact with something else. Anything you touch, there's a normal force between you and it. And the force that you feel is in one direction, and the force that it feels is in the other direction. It's Newton's third law. They're both the same amount of force. Both you and it feel the same amount of force, but in opposite directions. The Earth isn't in contact with anything, so there's no normal force here. Would we draw the gravity force downwards? I'm just pointing out that there's students that will still do this, and it's just because of out of habit. This was so I got some students from last night. I already looked at some of the work from you guys. The normal force up. Nope. We're in outer space now. It's easy to go back into habit, and I get that, but gravity force down. Nope. Nope. This is when we're standing on the Earth. We draw the gravity force down because the center is down of the planet Earth is here, and Earth's gravity pulls you towards that point. Right? If you're turning this sideways. And now you're saying, here's the Earth over here, and here's you over here. Draw the free body diagram sideways, right? You're being pulled sideways. I'm not saying it's obvious. I'm trying to teach you that. Don't feel bad if you didn't get it right. But the gravity force would really be in this direction. And it's easy, even I say the sun's gravity or I say the Earth's gravity. It's actually both of their gravity. Like, they both pull on each other actually with the same amount of force. Gravity is just something that, remember, because all forces come in pairs. That's what Isaac Newton said for his third law. Anytime there's a force, well, there must be something else that feels it because they only come in pairs. So it's easy to say the sun's gravity or the Earth's gravity, but really it's the mutual gravity that they have that pulls on each other. Another common mistake would be to draw the force that the sun feels. My apologies, I didn't mean to say that. Another common thing is to, if this was the, well, yeah, it's fine. If this was the sun here, to draw a small force felt by the sun, and then a large force felt by the Earth. Very common. Labeling them force of gravity on both. Because a lot of people say, well, the sun is so big, you can't put a, it doesn't feel a lot of force, it's so big. It's actually the same amount of force they both feel. It's Newton's third law. Another common thing, student might leave this blank and only put the force vector on the Earth. They're equal and opposite. So these force vectors should be pointing towards each other, if I drew it a little more cleanly, with equal length on a free body diagram and opposite in direction. Still not exactly the same. Not doing a very good job of drawing, but they should be pointing towards each other, equal in length. So I don't know what you did, but this is for you to kind of think about what you put. Another comment is if someone said draw the velocity vector, because there's opportunities on an AP exam where they tell you to draw things, graphs, pictures, all sorts of things. How would you draw the velocity vector for this position, assuming that the planet's going in this direction? Velocity vector goes this way, right? Tangent to the path. If they showed the picture of the planet over here, said the planet's going around, draw the velocity vector at that point. It's the instantaneous velocity vector at that point. Always tangent to the path. All right, so now we're gonna put it all together. Here's the sun, again, in the middle. We know that the Earth needs an inward amount of force equal to mv squared over r. Because this Earth is going to go in a circular path, and it needs to feel that inward pull. The requirement is the mass of the Earth times the speed of the Earth squared times r, which goes from the center of the sun, by the way, out to the center of the Earth. So whenever in physics, astrophysics, when we talk about r, it would be easy to say it's the distance from the surface of the sun to the surface of the Earth. That actually ended up being off, and you'll end up getting wrong answers. R is the distance from the center of one object to the center of the other object. That's considered r. So that's how much force the Earth needs. We know that they pull on each other with what amount of force? This amount of inward force is equal to the product of their masses, m1 times m2, multiplied by a constant, the gravitational constant, divided by that distance squared. So that is Isaac Newton's universal law of gravity. That is the pulling force, and wow, it just happens to be exactly what the Earth needs. That's amazing, right? Think about that. Think of how delicate so many things in your life are, and I don't mean your emotional life, and I don't even mean to our day-to-day life. I'm just referring to the physics and science. Think how delicate your human body is, all the systems in your human body, how they work so nicely, all the organs and all the things that if one thing is just slightly off, you're in trouble. Like, you might be dead, in fact. Like, they all have to work just so perfectly, and wow, they do. When you're looking at an outer space, you're saying, wow, it's all so perfect. It's such a delicate thing. If we were slightly closer to our sun, of course, everything would burn off. It would be too hot. All the oceans would evaporate. No life would be here. If we were further away, it would be too cold. It would be a snowball Earth, and everything would be frozen. We happen to be right in that right spot where water, liquid, can remain liquid. Just so nice. So delicate as well, where the amount of pull that the Earth needs that requirement is the mass of the Earth, the speed of the Earth squared divided by r. And it just happens to be that the amount of force that the sun provides GMM over R squared, where M is 1M and M is the other, is exactly equal to what it needs. If it was slightly more, if the Earth said, sorry, I'm going to pull on you with a little bit more than you need, I'm going to pull on you with a little more than mv squared over r, what would our planet do? The amount it needs to stay on this circular path at this distance is mv squared over r, but the sun says, I'm going to pull on you harder than that. Well, that more inward pull than necessary, this is what our planet's going to do. Go in circles, spiraling in, getting closer and closer until lights out. Interestingly, you go into the light to get lights out. That's what would happen if there was more pulling force towards the sun than the required amount, which is mv squared over r. What would happen if the sun couldn't pull with that amount of force? If the gmm over r squared ended up being a little less than the mv squared over r that it needs? Well, yeah. What would it be? Go ahead.
We would fly off.
Yep. But actually, more specifically,
it would slowly,
each time, we start spiraling outward. Yep. Each time, each revolution, we get a little further away, And each revolution is a year. And that means each year the sun would look a little smaller during the day and a little smaller during the day. Every year, wow, what's going on with the sun? It looks smaller every day. Wow, it's starting to get cold. Well, that's the delicate balance that we're in. And if this gravity force was just a little stronger or a little weaker, big problems. Wow, it's just so nice. It happens to be that these are exactly what they need to be for us to stay at this distance. Wow, that's amazing. Wonder what causes that. Don't know. Either way, we can, again, set these equal. And that was, I think, the hint that I gave you. So let's do that. The gravity from the sun. And again, if you know how to do this, bear with me. I had some people in the other class sleeping, And I looked at their work and I get it because they got it, they understood it all, they did it all. But there was also kids in the class that they did it. I looked at their work and they didn't understand this. And I have to review this stuff so everybody understands it. So again, if this is something that already fully makes sense to you, then bear with me. The gravity from the sun has to be equal to what Earth needs in the inward direction, right? The gravity from the sun is actually the product of the mass of the sun and the mass of the Earth divided by the distance between their centers squared. And the amount that the Earth needs is the mass of the Earth times v, the speed of the Earth, divided by r, v squared over r. I do have some people that I looked at their work and I saw an M1 in their work, an M2, and an M moon. Your homework problem was about the moon. And I looked at their formula like this and I saw 3 M's. I saw an M1, an M2. So I didn't know if that student was making that connection, and I want to make sure that's clear. M1 can be either one of these things. You can make it one of the masses, the sun, let's say. M2 would be the other one that's going around it in orbit. Maybe it's the Earth. As soon as you pick those, there's no third one, right? Those are just placeholders. M1, M2 are just placeholders until you say, let's make them something specific. Right? Mass of the Earth, looks like when you divide both sides by mass of the Earth, it cancels away. Now goal was to solve for V. Create a formula that you can use to solve for the speed of a planet without using a stopwatch. Because technically, you could. Technically, some of the ancient astronomers did that. They actually took note of a certain planet in our solar system in the sky of exactly what the position it was in. And then each night you go out, that planet at the same time, if you went, let's say exactly at midnight, you see Mars in the sky and you sketch where it is. You go out the next night exactly at midnight and Mars is slightly to the right of that. You go out the next night and Mars is slightly to the right of that. And every night at the same time you go out and realize that planet's moving. Of course it is. And they would literally come back every night and wait until it returned to that same spot in the sky. And by doing that, they've timed how long it took for that planet to go around the sun once. And so they could literally time it. They could literally time how long it takes a planet to go around by literally doing what I just described. Using this method, you can get the speed, because they would work out the speeds if they knew the time. You can get the speed without the time. So we'd have to multiply by r to both sides. R's cancel out. You notice there's an r on the top and an r on the bottom. You can think of that as over 1, if that helps you. Fill that placeholder. Now we have an r to the 1 here. This cancels with one of these. Now I'm just left with my v squared on the right. That's great. Let's just reverse the order and put it on the left, because we usually read this from left to right. V squared is equal to g times m. Don't confuse capital G with lowercase g. This is called gravity constant. And since there was one here, there was one of these left over after I canceled one of those. I have it over r. And then I just got a square root. My square root and my square undo each other. And that's the result. So the speed of any planet, important for you to know this can be used for any planet, is equal to g times the mass of what's actually called the host in physics, astrophysics. They call primary star in the center of that system. That's called the host. So the mass of the host is again the mass of the star. For us, we call that the sun. We divide by r, and remembering that's the distance from the center of the sun to whatever planet you want to find the speed for. And we square rooted it, and I'm going to write it as to the 1/2. So that's the formula. You could have used this for the moon. This would be the original problem on the homework said, find the speed of the moon. Well, who's the host for the moon? The Earth, exactly. So this would be v moon. This would be the mass of the Earth, and this would be the distance between the Earth and the moon, from the center to center, technically. And you could look those up. You could look up the mass of the Earth and the distance between Earth and moon. And you can find this value g by looking it up. You plug them all in. And I did that, by the way. The solutions I've already posted just before class started. Posted the solutions that I did all out in the assignment section. Come out as, when I did it, 1,020 meters per second. This was for the moon now. You know, I wrote this for any planet. When I did it for our moon, it came out as 1,020. And then when I looked up the speed of the moon, it said 1,022. It was almost exactly correct. So that's the formula. Let me move over to another page. I would comment that it's worth seeing what the relationships are. Specifically, the whole lab that you did, which was part D, was what is the relationship between the speed of a planet? We've got 8 of them. I like to say 9 because I still like Pluto, but it's not on our list anymore. What is the relationship between the distance to a planet and the speed of that planet? And that distance is the distance from the sun out to that planet. These are on opposite sides of the equation. One's in the numerator, one's in the denominator. That tells us these are inversely related in some way. Meaning a greater distance from the sun doesn't make a greater speed for that planet. A greater distance for the sun makes less, the opposite of greater, which is less of a speed for the planet. So that tells us Mars, which is a little further away from the sun than us, twice as far than us, goes a little faster than Earth or goes a little slower than Earth? Here's Mercury. Mercury's speed. Well, I will point out that, no, I won't show it yet, but Mercury has a certain speed. It ends up being the fastest in our solar system, zipping around the sun fast and moving with a speed in meters per second faster than any other planet. No, remember that near the sun, the gravity of the sun is strong, much stronger when you're close. Like a piece of metal close to a magnet is a lot of force. And you can think of that force causing a lot of motion if you want to think of it that way. Great speed for Mercury. Venus ends up being a little slower. Earth ends up being a little slower. In every planet you go out another orbit, you're further away from the sun. Jupiter, a little slower. Saturn, a little slower. Uranus, a little slower. Neptune, a little slower. And every time you go further away, that speed decreases, and that's because that's what this is suggesting. Larger distance away, less speed. How would we write that relationship? To identify a relationship between two variables, you cross out all of the other things, and you just look at what's left. V, then I write the proportional symbol to it instead of the equal symbol. And wherever there's something that's a whole, I just put the number 1. But don't forget to apply whatever's out there. This r is underneath the square root. That is how it would be written in a textbook. The speed of a planet is inversely proportional to the square root of the distance between the sun and that planet. I know it's a mouthful, but that's how it would be written out. If that's true, what would this graphically look like? You have a solar system, you're like, oh, we have one. How nice that is. We have all these planets. These are all data points for us. And if we can look up the speed of each planet, which was part of your lab, and how far away that planet is from the sun, which we have all that data, and we plotted it out, what shape should it look like? If you're an experimentalist in science who are not interested so much in theory, they're more interested in just taking the data and making measurements, called experimentalists, you'd say just grab the data and plot it. If you're what's called a theorist in physics is not so interested in experiments. They're interested in the math. And usually the theorists do math and feed their people that do the experiments and say, go look for this. In fact, a black hole was first predicted by an equation. And everybody says it's crazy, it can't be real. So that's what the math says. That's what Einstein's formula says. It says there should be something that is so massive it rips through space and creates a black hole. They've fed that equation and that information mathematically to experimentalists, and they kept looking and looking and looking, and sure enough, they were right. There's a black hole, right? That's how the experimentalists and the theorists work. They work as a team. Theorists are interested in this stuff. Experimentalists are interested in measurements and doing the experiments. So from an experimental point of view, you'd say, just take the data that's online and plot it. And you guys did that. A theorist would say, I don't do that stuff. I just look at the relationship and I just graph the relationship. What would it look like if it was V is proportional to 1 over R? What would that look? It's not. It's 1 square root of 1 over R. But what if it was? What would that look like? Just a standard inverse relationship like this. What if it was, so I'll write that, 1 over R. That's what 1 over R would R. What if it was 1 over R squared? It's not. Again, it's square root of 1 over R. What if it was 1 over R squared? This is your 1 over R squared. It just goes down more quickly because the bottom is being squared. That reduces the whole ratio very rapidly. Comes down real. Same shape though, I'm pointing out. What if it was this, what it is, the square root of 1, which remember is, this is R to the 1/2, right? So when we started with 1 over R, that's R to the 1. Then we looked at 1 over R squared, which is this one. And now we're looking at 1 over R to the 1/2. The exponent went from 1/2 to 1 to 2. So what would that look like? Same shape. It just doesn't go down as quickly as the others. This is a 1 over R to the 1/2. And that R could be an X. In a math class, these would be Y, and this would be X, and these would be X's. So theoretically, the shape should be that, what it is. That shape, something along that shape. I will bring it up online now just to show you. Yeah, many of you got this. Not everybody, but many of you did. Many of the students did. I'm going back to Google Classroom, and I'm going over to the instructions. And there it is. So, oh, couldn't preview. Oh, there it is. So there's mine. That's mine. And I labeled them. I put miles per hour just because I thought it would be cool to see, because we are Americans, of course, and we love miles per hour. So I did the speeds in miles per hour. Usually it would be in kilometers per second or meters per second in astrophysics. Anyways, I put them in miles per hour, and that's it. Mercury is 110,000 miles per hour. That's how fast it moves. More or less the same speed all the time. Venus, 80,000 miles per hour. Earth, 66,000 miles per hour, and so forth. Pluto, way out here. AU, by the way, stands for astronomical units. 1 astronomical unit is the distance between Earth and the sun. It's about 100 million miles, a little less than 100 million miles. It's such a big number, they said, let's just call it a new thing. Let's call it 1 astronomical unit, the distance between Earth and the sun. And that works out because Mars is actually 2 times further away from the sun than we are. And so there we say Mars is 2 astronomical units away. And we'd say Jupiter, as you can see, is 5 astronomical units away from the sun. Saturn is 10. Looks like there should be something here at 15, but the belief is that that planet probably got broken into millions of pieces from some collision causing the asteroid belt, right? You can see the pattern, 5, 10, oops, 20. Why is that? is there something, well, again, with all those rocks floating in that area, maybe that used to be a planet. 20, and Pluto, 40 astronomical units away, 40 times further from the sun than we are, way, way out there. But as that distance gets greater and greater, you can see that the speed drops dramatically. The speed of Pluto looks like it's in between 0 and 220,000, so it's about 10,000 miles per hour, much slower than Earth, which is 60,000 miles per hour. So that is the shape. So now I'd like to see if you can answer a question. I'm going to put you into a group breakout room to see if you can use this proportion. So if you don't mind, Zoe, getting your Chromebook out. Again, the concepts, the shapes of the graph definitely come, this kind of, I'm pointing out, I generally am really emphasizing the concepts and the drawings and the equations for sure, but I'm telling you again, there's very little actual calculation on the AP exam. It's a small amount. It could be it could even be zero. It could even be zero. So I'm going to give you a problem that's more like what shows up on the AP exam relating to this question. I'm going to throw you into a breakout room. Because they often, for a multiple choice, give questions to see if the students can apply these mathematical relationships. That's why I spend so much time not only talking about the mathematical relationships, but hopefully helping you learn how to figure out what they are. Because you're not going to memorize them all. I promise it's, well, very unlikely. If you can, that's a remarkable thing. So you can jot it down, then I'm going to drop you into a breakout room. I'm about to jot it down, if I can just get my camera back. So what would be, and for whatever reason, they very rarely mention planets in any of this conversation on free response questions. I don't know why. I think it's a perfectly good topic. I think it could be. Historically, when I look at their exams, almost never. It always shows up in multiple choice questions, almost never in free response. Don't know why. But what would a typical free response question look like? I'm going to show you. You can jot it down. Something like this. 2 planets orbit a star in a circular path. Planet A, they like A and B, as I'm sure you've learned that, A and B and 1 and 2. Planet A orbits at a distance RA with a speed VA. This is how they like to write. I'm sure you've seen this. 2 planets orbit a star in a circular path. Planet A orbits at a distance RA with a speed VA. Planet B orbits at a speed, you guessed it, orbits at a distance RB with a speed, better writing, but this is what they would say, with a speed VB. F. Planet B is, now let me choose this carefully. If planet B is 4 times further from the star than planet A, if planet B is 4 times further from the star than planet A, which expression below is correct? About their speeds. So it'll be a question about distance and speed, just like our lab just was. And what would they have? What would their choices look like? Well, I'll show you. They'd have something like VB equals, let's start with 1/4 times VA. Choice 2, VB equals 1/2 times VA. Choice 3, VB equals VA, where V again just stands for their speeds, the planet speed. B for planet B, A for planet A. This is saying that they go at the same speed. This is saying, planet B moves with half of the speed of VA. This is saying that planet B moves with only a quarter of the speed of planet A. All right, let's keep going. Let's do VB equals 2 VA. And they usually have only D parts, but I'm going to put more because I want you to be able to sort through them. VB equals 4 VA. And lastly, VB equals 16 VA. I don't know why I'm talking like I'm a French or something. VB. I'm not sure where that came from, but I feel like I'm French for a moment. Those are the choices. Again, they would not give you more than 4. Oh wait, did it get turned? Is it 5-ish? 5 as of last year? I'll look at it while you're working on this. Starting to think that actually they might have changed it. It always was 4. Did they change it to 5? Or was that just for the select 2? I'll look into that. Anyways, you guys can work on this. I'm going to put you into some groups. Let's give it a try. 1, 2, 3. How many? 1, 2, 3, 4, 5, 6. And Zoe's there. Cool. All right. Joey, maybe you can be like a fly on the wall and just kind of listen in on one of the groups. That should work. All right. I'm sorry, I have to cut you short. So I still need to teach you something else. So sorry if I cut you guys short in your conversations, but I would like to go over that at this point with you. Now, if you're unsure about a question as you take the AP exam or any of my tests that are AP questions, and you're looking at a multiple choice question, the idea of eliminating things that you know are not true is a massive, step in the right direction. If you remember that in outer space stuff, everything becomes less further away. It's one thing to remember. I guess not everything. The time for Pluto to go around the sun is 200 years, so that's further away. That didn't become less. So other than time, in this case, the period that I was referencing, certainly anything to do with speeds and anything to do with forces, they all become less as you get further and further away from a star. So in this particular case, we know we're being asked to think about two planets, one that's further away. The one that's further away has a speed VB, so it has to have less speed because it's further away, because that's something we actually just saw in the graph, right? Planets are further away, have less speed. So which one of these reflect that idea? This says that they have the same speed. This says that the further one that's further away has 2 times greater of a speed than the closer one. This one says it has 4 times greater of a speed than the closer one. This one says it has 16 times greater of a speed than that can't be. Now we're down to these two, because these are the only two that represent the idea that the speed of the furthest one is going to be less than the speed of the first one. This is saying that the speed of the further one is 25% of the speed of the first one, or 1/4. This is saying the speed of the further one is 50% of the speed of the closer one, or 1/2. So we want to see how we can apply this relationship. V was proportional to the square root of 1 over r. What if it wasn't? Or what if a student in the exam says, I think it's V is 1 over r. I remember an inverse relationship. I remember the graph. I think this is it. What if it was this? Then they're inversely related. If r goes up times 4, because I believe that's what the question said, then one of them is 4 times further away than the other one. So if we can increase r by a factor of 4, v isn't going to go up. They're inversely proportional. V is going to do the inverse of go up, which is go down times 4. When we say go down times 4, that means, again, divide by. We're going to divide by 4. If this was the correct relationship, you'd conclude that A is the correct choice, that the speed will be 1/4, because you're taking it and dividing by 4. Down by 4 means divide by 4. However, it's not. This is the physics says that this is actually the correct relationship. So let's do the same thing. If r goes up times 4, v isn't going to go up. There's still an inverse relationship here. More of one is making less of the other. V is therefore going to go down times. But now you got to think, all right, I'm going to put the 4 in for r. And just look at that 4 now and think there's a square root over that 4. It's going to go down times root 4. Well, what is root 4? It's 2. So that means the speed is going to go down by a factor of 2. It means we're going to have to divide by 2. Or you can say the speed will be a half of what it used to be when you were 4 times closer. Go 4 times further away and you'll only have half the speed. So the correct answer is B. All right, I'm going to teach you something similar but different, somewhat different, that you absolutely have to know. So if you want to jot some of these notes down, you can. I'd recommend it, but it's totally your call. What we're now going to be talking about is g, lowercase g, at different points in space. All you've really been taught about so far in all of the physics stuff you guys have done with me, which is a year and a half, all you really know about g, for the most part, and I'm not trying to belittle you or anything, I'm your teacher, is that anywhere you live on the surface of the Earth, g is the same. That for people in Australia right now that are doing having the same class and the same discussion, and maybe even doing the same science experiments we're doing, when they get their value from g, perhaps from the slope of one of their graphs, it says 9.8 for them too, right? And that's because, well, that was the center, from the center out is the same distance everywhere, right? So it's indicating that as long as no matter where you live on the Earth, as long as you're the same distance from the center of the Earth, g will be 9.8. What if you go up to the top of a mountain and decide to do an experiment up here? You think it'll still be 9.8? You go to the top of Mount Everest?
Yes.
Anybody else? We have one yes. You say no. What do you think? More or less? So what do you think? Less, yeah. Good. It is actually less. So just think of it this way. When you get further, gravity works in that way. Further away you get from a planet, the weaker the gravity of that planet is on you. It pulls on you less hard and less hard and less hard the further and further you get away. It's like magnetism. 2 magnets close, boom, strong pulling force. Separate the magnets a bit, you'll feel a lot less pulling force. Separate them even more, you don't even notice it anymore. It's a force that becomes strong at close distances, weaker at far distances. And g is a representative of the strength of the planet's gravity. If g is a number that's less, like 9.75 on the top of Mount Everest, that indicates that g, the strength of Earth's gravity, is a little less there. Not a lot less, but a little less. And they've done experiments and proved that, sure enough, it's correct. And the equation I'm going to show you predicts that that would be the value on the top of Mount Everest, and they've done some similar things and realized it's exactly what the equation says it should be. So what I'm about to show you is the idea that you can calculate, because my point is, does Earth only pull down on you when you live on Earth? Do you only have weight when you live on Earth? Well, what about when you go to the top of a tower? Does Earth, because Earth isn't touching you when you're on the top of a tower, do you still have weight on the top of the tower? Yeah. What about if you're an astronaut in outer space? Do you still have weight?
Yes.
Is Earth still pulling you down? Yep, sure is. You still have weight anywhere because the force of Earth's gravity is called your weight. That's what weight is. It's the force of Earth pulling you towards it. it just turns out that as you get further and further away, that pulling force becomes less and less and less. If these were the gravity force vectors, you'd see that at all these different points in space, as you get further and further away, it pulls on you with less and less and less. So G becomes less and less and less, and therefore your weight, which is m times G, becomes less and less and less. How do we figure out what that formula is? You have to, unfortunately, because it's needed on a lot of their multiple choice questions. So I'm going to show you. Not too bad. It's not too hard to derive it, actually. It's one of the easiest ones of all year. Here's my guy.
Mr. Herzog, I'm not presenting
Yes, sir.
again.
Oh, so sorry. Jeez. Wish somebody said that. My apologies. We'll come back. That was important. You seeing what I was just drawing was important, so I have to go back to it. This is what I was showing. I was showing that on the surface of the Earth, the value 9.8 is the same all the way around the Earth where you live, in Australia or some other country, because you're all the same distance from the center of the Earth. On the mountain, when you climb up to a mountain, you'd see that the value on top of the mountain is actually a little less than 9.8 because you're further away from the Earth. G, remember, the number lowercase g tells us how strong the planet's gravity is. And then I said, if you were on top of a tower, do you still have weight? If so, that's because the Earth is still pulling you down. And you're not Earth isn't touching you when you're on the top of a tower. So that shows us that the Earth doesn't really care if you're touching the Earth or not. It'll pull on you no matter where you are. What if you're an astronaut in outer space? Absolutely. If someone just dropped you here, guess which way you'd start to go? You'd start going towards the Earth, gaining speed, accelerating, because there'll be a net force on you. The Earth's gravity would not be canceled by anything else, and you would gain speed faster and faster and faster and faster. Wait, isn't that what happens when we drop something? Yep, that's totally what happens when we drop something. It gains speed as it falls, right? You would still gain speed. However, you would not gain 10 meters per second of speed each second if we dropped you in outer space. You would gain some other amount of speed per second. It depends on what G is out there, and that's what I'm about to show you. How do we find G? We know that the weight of anything, which is the force of gravity, is m times G. We're back to 9th grade physics. One of the first things I teach. Then we come along and say that Isaac Newton has this other fancy equation for the force of gravity. So we actually have two ways of calculating the force of gravity, known as weight. For me, when I put my mass, which is about 80 kilograms in, and multiply by G, which is about 10, I weigh about 800 newtons. And I have a force scale actually right here. You've probably seen me stand on it before. It says about 800 newtons. It means you have to lift upwards on me with about 800 newtons of force to lift me. Interestingly, if I use this more fancy equation and I plug these numbers in, you don't have to remember the value for G. Actually, it's on their equation sheet. I don't think you'd ever need to use it, but it's a constant, gravity constant. If I plug the mass of the Earth in, which I can look up online, plug it in here, and I said, well, let's make the two objects the Earth and me, because I want to use this equation to calculate my weight. Will it work? Well, you could try. I would plug in my mass of 80 kilograms for one of them. The other object, I'd have to look up the mass of the Earth and stick it in. I'd have to look at, well, what's the radius of the Earth? Because how far away am I from the Earth? Someone might say, what do you do with the R? You live on the Earth. You're touching the Earth. R is 0. The distance for R is the distance from the center out to wherever you are. How far away are you from the Earth, so-called? Well, about 4,000 miles, because it's from the center of the Earth. Gravity kind of comes from the center of a planet. So you could look that up, and you can put it in. You could do this at home if you were interested. If I did it for me and plugged all of those numbers in, with one of them being my mass, guess what number pops out of the calculator? 800. Say, wow, that's fantastic. That's amazing. Yeah, that's an amazing stuff that Isaac Newton came up with. Sure enough, this formula tells us that the gravity force between the planet, Earth, and me is 800 newtons. Or when I use just m times g, it's also 800 newtons. And he said mg, by the way, had to be correct because F equals ma. He said any mass times any acceleration needs to be a force. So on a planet, acceleration due to gravity times m must be a force, and we're going to call that your weight. So since these produce literally the same number, that means they're two equivalent expressions for the same thing. They're two equivalent expressions for the force of gravity. They're two equivalent expressions for your weight. So all we have to really do is say the expression 1 for the force of gravity is equal to the expression 2 for the force of gravity. What's expression 1? mg. Your mass times g. And then let's use the other one that he gave us. G times the mass of the Earth times the mass of you divided by r squared. Just remembering that r goes from the center out. You'll see that mass of you cancels away, and that's all you have to do. You're left with the formula that says G, or that planet, depending on how far away you are, is equal to the constant of nature called the gravity constant, how massive the planet is, divided by how far away you are from the center of that planet squared. That's literally it. That's all you do to derive that formula. You could look it up on Wiki and you see this is it. So what does that mean? I'm going to show you because I want to give you maybe a short assignment tonight because I know where I see you tomorrow. But one short assignment potentially to use this formula. Might be just a couple questions from AP Classroom. So it means that if someone said, here's your planet Earth, and we want to know what the value for G is out here, for Earth's gravity, it's not 9.8. That's when you live on the surface of the Earth when you're a distance of r away from the center. Now you're way out here. Your distance from the center is much larger. So technically, we could use this formula and calculate what G is out there as an astronaut, if that's you out there floating as an astronaut. And a typical question for AP Classroom would say, here's an astronaut floating in outer space. Their mass is 50 kilograms. What is their weight? They know some students are going to do 50 times 10, and so one of their choices will certainly be 500, and that's not the right answer. What is the weight of the person out here? Less. They weigh less because G is less. How do we find out what G is? They'd have to give us the distance from the center of the Earth all the way out to the astronaut. You'd say, God, that's a lot. You're going to make those calculations? No. Like Joey said, you almost never make a calculation. So how do we do it? If they told us that this guy is 50 kilograms, then before he goes into outer space, what does he weigh? What is the gravity force? 50 times 10, he's 500 newtons before he gets into the spaceship. Then he flies out to a spot that they call 2r. If this is 1 Earth radius, he decides to go away from Earth another Earth radius for a total distance of 2r away. That means as a result of being out here, he's twice as far away from the center of Earth as he was when he was in his house. How can we answer what the weight, or if they asked us what G is, what is G out here? Or they could ask us, what is his weight? Similar question. All comes back to proportions. What is the relationship between G and R? Proportional symbol. Cross out other things and just focus on what's there. And there's a hole, put a 1 in its place. G is inversely proportional to the square of the distance. What would that technically look like if we graphed it? G versus R, if you went into outer space and had a G meter and collected data points as you kept going farther and further away and then plotted it on a graph, well, it's a 1 over R squared. It would look like this again. So let's use the proportion. In the problem that they would give you, they'd say that the astronaut is 2 times further away from the center of the Earth compared to when he lives in his house. At R, now he's 2R. All right, if R goes up by a factor of 2, what will G do? G will go down times 2, imagine putting a 2 here now, for R, times 2 squared, that's times 4. That means G will be reduced by a factor of 4. That means we'd have to divide by 4 to get our new value for G out here. Well, if we know 9.8 is the value here, how do we figure out what the value is here? 9.8 divided by 4. The value for g out there would be 2.45 meters per second squared. That's what g is out there. If they instead ask, what does this guy weigh out here? His weight is his mass times whatever g is in that spot. 50 times 2.45. Definitely not 500 newtons. That's what he weighed back at home, where he's in a stronger gravity environment. Out here, he's in a weaker gravity environment. Since gravity produces our weight, his weight will be less. But again, they'll have one of the choices as 500 newtons as a little worm that they're dangling in front of you to see if you'll bite for it. 50 times 2.45, only 122 newtons. It came out as 122.5 newtons. Far less, weighs far less than 500. In fact, how many times less? Four times less, right? Everything reduced by a factor of 4. So he weighs 4 times less. What does that mean? Lastly, it means if you could imagine having some giant tower that literally went all the way into outer space, out where he is in this original picture, you're like, let's just build a building that goes all the way out there. Cool. Let's put our bathroom scale on it, and then let's stand on it. Way out where g is only 2.45 meters per second squared. And I go out there with a spaceship and get out of the spaceship, and they lower me down, and with my own bathroom scale, what will it read? On Earth, I'm actually 200 pounds. I'm 200 pounds right now. What will it read if I go out there? Any guesses? Remember, it goes down by a factor of 4. 2 times further away is 4 times weaker gravity, 4 times less weight, 4 times less than 200 pounds. What is something that's less by a factor of 4 for the number 200? Be 50 pounds. I'd only weigh 50 pounds out here. That would be my weight. If I then hold a rock, and these are my hands, and I let go of the rock, after 1 second of falling, what will the speed of the rock be? In this hypothetical giant tower that goes out way out there, and I say, I'm here. Cool, let's measure it. Yep, wow, sure enough, I'm 50 pounds. Let's drop the rock. Remember, g out here is this value. What will the speed of the rock be after 1 second?
2.45.
You got it. 2.45 meters per second. Not 9.8. That's only when you live over here on the surface of Earth. It will give you that amount of speed in 1 second. After 2 seconds, what would the speed be? 2 times 2.45. I guess 4.9 meters per second. And you'd gain, the rock would gain that amount of speed each second. Same ideas from kinematics still apply. It's just that the rate that you speed up is a lot less. Why? Because the force that's causing that acceleration is a lot less. Why? Because gravity forces get a lot less when you go further from them. That is the last part of what I wanted to show you, and I just barely finished it in time. Nope, a few more minutes. I see it. I'm going to let you think about one more problem on your own. I'm going to give you one on AP Classroom. I'm going to post it right now. I'm going to project it right now. Let's see if you can try one. Let's try this one. No, we won't try that. Although that one might be one of your homework problems. Let me try a different one. Ooh, this is it. Yeah, I don't want to do that one either. Maybe for tonight. Do that one. Sorry, let me find one different. Ooh, let's try this one. All right. I will zoom in since I know, Zoe, you probably can't see it. Although if you have your screen, can you see it on your screen, Zoe? What's that? It's really small. Yeah, I'm sorry for that. I'll read it to you, to everybody. It says a satellite of mass m, a satellite. I was talking about an astronaut, but it could be a satellite. It could be anything. It could be a space rock, anything out there. Doesn't matter what it is. A satellite of mass m orbits a moon of mass capital M in uniform circular motion with a constant tangential speed of v. Remember that the tangential speed is just a fancy word for the idea that that speed, velocity vector, I should say, is perpendicular to r. It's not important, really, not right now at least. The gravitational field strength, g, at a distance capital R from the center of the moon is GR. That means the strength of gravity on the surface of the moon is, we're just going to call it GR. The satellite is moved to a new circular orbit that is 2R from the center of the moon. What is the gravitational field strength of the moon at this new distance? Totally an application of what I was just showing. You can think about it. This is an example again of problems you get. So they're saying there's a satellite out in orbit, and G in that spot is just called G. Then they double the distance. They bring the satellite twice as far away. What is the new value for G out there? Well, if you're not sure, remember, just use the logic to at least eliminate some things you know it's not true. Does G get stronger or does G get less when you go further away? Weaker, right? So which ones can it not be? Yep, can't be C, and it can't be D. That's saying that G is 2 times stronger way out there, 2 times further away. D is saying that G is Earth's gravity is 4 times stronger way out there. Wait a minute, that doesn't make sense with our intuition, or maybe which is what we learned, that gravity always is less when we get further away. So it has to be A or B. How do we apply that proportion? Remember, G was proportional to 1 over R squared. It's an inverse square relationship.
Would the answer be A?
Yeah, it would, Jaden. Why do you say A?
Because it's inversely proportional and it was moved by a radius of 2.
You
So
got
therefore
it.
it would be 4 times as less.
Nicely done. Totally correct, Jaden. Nicely done, Jaden.
Thank you.
Yep, A is the correct answer. So remember that with gravity stuff, when it's an inverse square relationship, when you know that something is proportional to 1 over something squared, or in this case, gravity is inversely proportional to the distance squared. 2 times further away, 4 times weaker gravity. 3 times further away, because they could have said 3 here, 3R. 3 times further away would be how many times weaker? If it's an inverse square relationship. 3
6
squared,
times?
3 squared.
Oh.
Good guess, 3 squared, 9 times weaker.
Oh,
4
yeah.
times further away, 16 times weaker, 4 squared. How would that look in this problem? G over 16, right? That means it's been divided by 16. It's 16 times less way out there. 5 times further away,
25.
5 squared, 25 times weaker. How would it look on this problem? G over 25. 10 times further away,
G over 100.
G over 100. Nice, Jaden. Good job. You got it. Totally right. Yep. And once you get that inverse square law idea, and some of you must certainly do, I know Jaden does, and probably others do already, you can apply it to a number of different things in physics. There's an awful lot of things that have that kind of relationship. 1 over R squared or 1 over something squared. It's called the inverse square law. Light, by the way, I'll give you one example. If I shine a flashlight right in your eye at some distance, like 2 feet away, you're like, "Oh, it hurts my eyes," and there's a certain amount of brightness in your eye. If I then take the flashlight and I bring it 2 times further away, if we were originally, I was only 2 feet from your eye and now I'm 4 feet from your eye, is the brightness in your eye 2 times less or 4 times less? Turns out that it's an inverse square relationship. And although my flashlight is 2 times further from your eye, it's actually 4 times dimmer. It's an inverse square law. If I brought it 3 times further away from your eye, it's 3 squared, 9 times dimmer in your eye. This is one example. Inverse square law plays a major role in a lot of things. All right, I'm going to end there. I will tell you guys, I want to give you just like a couple of these. I don't know if it might be all 6 of these, and if so, then that would probably be one of them. So I'm probably going to assign what you're seeing here. There's 6. That's all they actually have. They don't have more than that. I'm surprised. I figured they'd have more than that for this specific topic of planets and all that kind of stuff. So more than likely, I'm going to assign just these 6. So give them your best shot, and we'll talk about them tomorrow when I see you guys. Remember, tomorrow is Friday. Thank goodness we're already at the end of the week, but we'll have a very short 30-minute class. I still haven't done those last 10 questions, so I will, I promise, do them. I'll do them tomorrow. Definitely will. Just pointing out, the first 10 questions for the last quiz, they were recorded. I reviewed them all, and I put that video there for you. Been very busy, and I'm trying to catch up with things. So I'm going to do the last 10 questions because that Forces quiz was 20 questions. So I'm going to do the last 10 questions and post it soon. And I'll ask you guys to do something in terms of looking at. I mean, you can always ask people, and then some people will, and some people won't. I plan to do something so it encourages students to look at their questions they might have gotten wrong. So I'll have that up there for you soon. What else is hanging? Your circular motion lab from Pivot Interactive. Still haven't looked at it. Probably won't till Monday, more than likely. Is there anything else I can think of? Nope. Any questions from you guys? Nope. I will tell you good news. The AP curriculum board removed 3 units from what we need to do. Hallelujah. And for that reason, that's why we're on track. To be honest, I was like, I don't know how I'm going to do it. In a year like this, with such a little time that we've been given, they realized there was a lot of schools saying it's just not going to happen. We're never going to get through all that. So that was relatively recently announced. And so I'm telling you that I'm a little sad because, Joey, do you remember how much I love electricity? I love electricity. It's like one of my favorites. I really do.
Yes, I remember.
I love it. And we're not going to do that anymore. So I'm a little sad about that. But the point is, I don't know. I wouldn't have had enough time anyways. But anyways, they said, surprisingly, not just for this year, permanently, they said AP Physics 2 actually teaches electricity. And so they made a permanent decision that AP Physics 1 will no longer have electricity effective immediately. That was decided, relatively recently. And it wasn't just circuits. It was a lot of other things as well relating to electricity and electrical forces. And shockingly, another massive unit. Guess what, Joey? What the other unit is? That's totally gone forever.
Waves.
Waves is gone forever. Another beautiful topic that, like, oh. But it saved us. I'll tell you, it saved us. And for that reason, we're pretty much right on track. That's a huge cut. I'm just telling you. You don't think of it because you're a student, but as a teacher, like, that was huge. That's a huge cut that they just made. That's not just for this year, but forever. So that's good news because that's what we needed. So we're right on track. See you guys tomorrow, and I hope you enjoy the rest of the day. All right, bye, everybody. Bye-bye.
Bye, Mr. Herzog. Have a good day.
You too. Bye-bye.
Thank you. Bye-bye.
Just 1 second. Let me just close this.